So let's move on to Diana Valencia.
Yes, thank you. I'll jump right in so that in the sake of time. So can everybody see the presentation? I don't see people's face, but hopefully you can give me a thumbs up. Yeah, okay, awesome. Thank you. So I slightly changed the title of my talk to reflect the paper that we have in press, and we're going to put in an archive in the next few days. It's chemical fingerprints of formation in rocky super Earth data. And I want to acknowledge that the heavy work was done by my grad student. He's finishing his master's, Michael Plotnikov. And in a nutshell, what we wanted to do was compare the composition of planets which we think are rocky to the stars' refractory ratios, because it's been proposed that those two should match. And to a good extent, it matches in the solar system for the Earth and Venus. Mars is two different groups think differently. And Mercury, we know it doesn't match the refractory ratios of the sun. But in any case, it has been proposed for exoplanets that the refractory ratios, and for people that don't know about this jargon, is just the rocks that condense out of the solar nebula at very high temperature. So that's what we call refractory. And those ratios as seem like iron to silicon, iron to magnesium. Perhaps if the planets have a primordial origin, they would have the same as the star. So what we wanted to do is to see if the data was enough in precision and in numbers for us to test this and see any connections. So you see here the data, the radius versus the mass of planets that intersect what we call the rocky region. And we've only plotted the ones that we use, and our criteria was that their mass had to be better to 25% in error, and the same for the radius. And so we have like a handful of 30 planets. You see that this is the pure iron. It has a little bit of nickel as well, line, so we don't expect any planet to be denser than this. We have Mercury that has a core mass fraction of about 63%. We have the mass radius relationship for the Earth that has a core about 1/3. And then we have the maximum size a rock can have by extracting all the iron from the planet while keeping all the appropriate mineralogy. So we call it the rocky threshold radius. It differs from the magnesium, silica, oxygen that you have seen in other works, because we use all the appropriate mineralogy that it would have. And you can look at the paper for what the differences between the two assumptions is. Any planet above this definitely needs to have volatiles. Any planet below is possibly rocky. The more compact it is, the more likely it is that it's rocky. And we differentiate the planets that have error bars well within the rocky region as circles, and the planets that intersect this space where you have volatiles, because their data is consistent with them having a small envelope. And from mass radius measurements, we wouldn't be able to tell. Now, the advantage of just referring to rocks and assuming that all these planets are indeed rocky planets is that with mass and radius, these two data points, we can determine the ratio of mantle that's mostly made out of magnesium silicate rocks to core, which is mostly made of iron, and we include an alloy as well. So it doesn't become a degenerate problem. We remove the degeneracy and we can actually determine the composition of these planets somewhat uniquely. So what we do is that we use an internal structure model that is state of the art. It has all the mineralogy. It can mix all the different end members to make sure that we span all the relevant compositions. And it determines the radius given a mass and composition, and that in our case, it's determined by core mass fraction, amount of iron in the mantle, and amount of silica in the core. In the Earth, we know that there's a light alloy in the core, and there's different candidates. So we decided to look at silica because it would change the silica to iron ratio. But we let it vary between 0 up to 10%, because 13% though, because we think that that's kind of what the Earth has, about 10% a light alloy in the core. And then we use an MCMC model to sample the internal structure and try to match the mass with the uncertainty and the radius with the uncertainty that has been measured. And so what we obtain is the core mass fraction, the amount of iron in the mantle, the amount of silica in the core, and from that we derive these chemical ratios. So as an example, I want to show you 55 cancri E. You see the mass here and the radius here and how much we can constrain the core mass fraction, the different proportions of these minerals, and then the ratios are seen here. And you can see that the core mass fraction really influences the relationships between mass and radius. And so that's what we can, that's what we can constrain the most. And so we do this for all the 30 planets, and then we try to see if there's any trends. So the first thing we do is we plot them, the core mass fraction as a function of insolation. So here is very hot, here is cold, and again, we make a different distinction between the planets that could be volatile to the planets that are well within the rocky region, which is these circles. And this planet here is an LHS 1140 planet, which could have water, and we have not considered that as a possibility. All the other ones are too hot to have water that's not in a volatile manner. So these ones are better constrained, but you can see that this is not an outlier either. And so there's certain things that we saw that there is no clear trend. We're probably not seeing any planets here because they are, they're long period planets. We see that the very short period planets, you can have a long variation, and we'll talk about that later as more. But I want you to notice that there's some planets here that would have a very low core mass fraction and very irradiated. So if the theory of evaporation stands as dividing the planets that are volatile from the ones that evaporated to become rocky, then these guys here would have been evaporated, most likely, and the rocky interior would be iron depleted. And that is something to really ponder about because we don't have a theory to explain that sort of planets. We don't have a theory that would preferentially lose iron material to rock material just because the iron is in the core. But it could be that these are volatile planets. And if they're volatile planets, then why didn't they lose their atmospheres knowing that they are so irradiated? So what we're seeing is that there's these planets are revealing a lot of questions for us to follow up as modelers and observers. So I want to show you in this other space a comparison between what we found from the planets to the stars. So we looked at the stars iron to silicate ratio and iron to magnesium ratio, and you have that the results are in this red line. So this is the 1 sigma value of the distribution, and this is the 2 sigma values of the distribution. You see the marginalized distribution here. I want you to notice that this is in log scale. So this tail, for example, here extends much higher. These are the planets that intersect the RTR, and these are the planets that don't. And I want you to draw your attention to the big error bars. So, and they mostly come from poor mass estimates. In some cases radius, but in most of the times it's poor mass estimates. The yellow symbols are the iron to magnesium and iron to silica ratios of chondrites of meteorites in our solar system. So, well, there's the sun, but then you have ensitite chondrites, which are the most iron-rich and are a little bit anomalous, and you have the other ones. So you can see the spread in the solar system, you can see the spread in the planets, you can see the spread in the stars. Sorry, and you can, again, if we take the two samples of the planets as one, and you say all the planets in this regime, this rocky regime, then the comparison is this gray line to the red line. But if we divide the two from the ones that are well within the rocky region, though you see this green line coming up here. And the problem with looking at iron to silicon, iron to magnesium ratios is that it's a nonlinear ratio, so it exacerbates outliers. So instead, what we did is also comparing core mass fraction space. So this is another way in which we compare in the refractory ratios by bootstrapping our sample and taking into account the errors in the planets. And so you see that the planets are this gray line when they're taken together, and you can see planets that would be that have a tail that is at higher power at larger iron to silicon ratio. But the other way of comparing them is in this core mass fraction space, as I was saying, and it's doing the translation of the stars and saying, given that the stars have this ratio of iron to silica and the other ratio of iron to magnesium, if planets were of primordial origin, what would their core mass fraction be? And so that's what you see over here. And you can clearly see that there's a lot of planets that are very enriched in iron. And there are some planets that, if they are indeed rocky, they would be depleted in iron with respect to the stars. So this figure here, or even this one, just shows that planets have a much wider distribution than that of stars. And it's not surprising when you think about the solar system and think about Mercury. And so it calls into questions of using the refractory ratios of the stars as a proxy to what is the rocky interior of planets. And so what you see again in this figure, and now I can explain a bit better, is that this red shaded region is that comparison of translating the star's composition to what planets around them would follow if they had a primordial origin. And this is a very peaked distribution. Most of the planets would be right on this line. Some of them would be here, but these ones here are starting to be too far away to be explained from a primordial origin. The next thing we did is looking at samples. So the first comparison was looking at populations, because most of the planets that we have, there's whole stars, we don't have the information on the composition, but that's, we actually do have that for 4 systems. So we can do this one-to-one comparison. Let me see, just check the time. Okay. I think I'm too, oh, sorry, I'm going over time. I'll try to be quick. And so you can see.
You're not over time yet. You have a few minutes left.
Okay, perfect. Thank you. So, and this is really good for the star people, and the message I want to bring to you is that in some cases, actually, the stars, our knowledge of the stars is what's keeping us from making more better constraints. So, for example, you have 55 Cancri. This is the measurement of the 55 Cancri, the star, and this is where the planet would lie. So they don't seem like they match. It seems like 55 Cancri, if it is volatile, it would be depleted in iron. But refining the star would go a long way for our understanding of this system. You have this other multi-planet system, where is it, over here, which I think is a great example of what we might be able to do in the future when we have multiple planets, and we have planets that are, one of them is closer to the star than the other. I believe it's the purple one that is closer to the star, so it should not be volatile. Because it's very highly irradiated, but it is iron depleted. And so this is the one that, these are the type of questions that we need to dig a little further. And then we can compare them to the stars and see that they actually don't overlap as we would expect with a primordial origin. So if we have this kind of work with multi-planet system and we build a database, I think that that is a very fertile way to compare formation scenarios that produce the chemical compositions that we see. I want to move on to this figure, because this figure has a lot of information. So we wanted to introduce the uncompressed density to the exoplanet community. It's been used widely in the planetary sciences because it is a great way to just compare composition. So this is a figure where you compare bulk density or mean density that you've seen in other papers. And the problem with that is that the bulk density can change because of composition and because of compression effects or pressure regime. So for example, Mercury and the Earth have the same bulk composition, bulk density, but they have different uncompressed densities. And the uncompressed density, you can think about it as when you compress all the rocks up to a reference pressure and ask what would the density be and a reference temperature as well. Although for rocks, that temperature doesn't matter very much. And so what we did that exactly for our planets, and you need an internal structure model for this. And in this space now, we're really comparing apples to apples. And so in this space, this is uncompressed density as a function of radius. For a given radius, we are biased to observing higher uncompressed densities because it means that the mass is larger. So this region here is easier to observe than this region here, and so is this region here easier to observe because of higher radius than this one. So this here, we should be able to observe them, and there is a lack of planets here. And this is real, and what we think is that we're seeing really where the runaway gas accretion starts. We see that there's a variation in composition at this 1.5 radius, but it could be that it still extends to lower radians, but we're not sampling this as well because of observational biases. Given that we are likely to see everything here, perhaps these planets are showing us the maximum enrichment that you can attain from formation. That's an idea we want to put forward for everybody to investigate. And then the last point, which is connected to what I said before that I wanted to bring to your attention in this figure, is that the other thing we did was divide the planets among the ones that were very highly irradiated with these large symbols, mediumly irradiated, and cooler planets. And the radius valley stands between 1.5 and 2, and about higher values than 300 times the insolation from the Earth that Earth receives. So if you focus on the big symbols, this is where the radius valley stands. So remember, these planets also have masses and radius. So we see some of them here, quite a bit of them here. We don't see a lot of them here, again, because we're biased against them. But we do see that there's this highly irradiated planets that if they're rocky, they are depleted in iron. And we don't have a theory to form them. In fact, we don't have a reliable theory to form this very iron-enriched planets either. Another work with another student that I have, which we look at n-body codes, we find that these are very difficult compositions to achieve when you go to this large masses. So I think what we're hoping to do is build a database where we have very rigorous composition of the planets that are rocky to start producing these comparisons, trying to see trends in the data that then can feed our formation models. And the last thing I want to say is that in order to reproduce this figure, we have a GitHub repository so you can find, you can reproduce where the stars would be, you can find the iron to silica at all the planets. We make it easy so that you have mass and radius, you can get the core mass fraction, you can get the composition, etc. Because I know that internal structure models would be another layer for observers to use. So we have just made it very easy so that you can start using this uncompressed density or iron to silica ratios or core mass fraction to compare planets to the stars or one another. So for the sake of time, I'm just going to leave my summary here and stop so that we can discuss my results and what was proposed in this session.
Thank you so much.